To make an MBSE effort work, you need a lot of different types of skill sets that need to come together. So you need still your systems engineers, ones that are flexible enough to think in maybe a slightly different way and be both a system engineer and a model-based system engineer. You need your software folks who understand enough about your system engineering and your model-based system engineering to actually develop effective tools to help those people. And you also need a lot of buy-in from other parts of your project, so from your subsystems, from your project management, to make sure that you get the resources and the help that you need, right? Systems engineering touches everybody on the project, all the different systems, and so it's MBSE is an effort to has a broad reach, and having people that are open to it and flexible is also very important. The other part is picking tooling. So like I said before, a lot of times people think, okay, I'm going to do MBSE, I'm going to buy an off-the-shelf tool and it's going to work. Depending on the size of your effort, that can work for you. So if you have maybe a smaller MBSE effort where you're dealing with, a simple system and a handful of people, that can work. But at least with the current state of the practice on the tooling side, if you have a large scale deployment, you're probably going to have to develop a lot of kind of supporting scripts, a lot of supporting tooling. And so you're going to also need the people to do that and the resources to do that. So depending on the size of your effort, you may or may not be able to just take an existing tool off the shelf. You may have to develop it in-house. The other part is that, for example, places like here, JPL or others, right, you're going to have institution-specific standards that you need to follow to make sure that you're doing things, appropriately. And so a lot of times you're going to need to tailor MBSE tools and MBSE processes to fit your institutional standards. I think one of the challenges right now in terms of uptake is I can't just go, pull all that stuff off the shelf and say, yep, we're going to deploy it, and I have a long heritage of doing that. There's still a lot of exploratory work that needs to be done. You really need that whole ecosystem to be on board with that. I'll tell you that's a term that has a lot of different meanings to a lot of folks. When I think about it, it's just a way to represent something at a different level of abstraction. So, for example, when we think about physics models, so you think F equals ma, that's an abstraction of the actual physics of our universe. When we talk about model-based systems engineering, what we're trying to talk about is models of our system. So, if you imagine our spacecraft, well, I'm going to try to come up with some useful abstraction of that and call that my model. So it may not be a bunch of equations. It may look more like a bunch of blocks and lines. It may look like a lot of different things, but it's just a useful abstraction of the thing that we want to talk about. We've had a lot of success actually tying our kind of descriptive model of our spacecraft system with analytical models of various things. So, for example, analytical models that look at the power, analytical models that look at our trajectories and things like that. And so basically that structural model of the spacecraft system has all of your key parameters in it, while those analytical models may have the math. And so there you have a nice blend, and it's been effective to do that. Sometimes we run into issues with people feeling like they don't own those parameters anymore if they're in that descriptive model, but usually the value proposition of saying, well, we're going to update that parameter in one place, and all these different analyses are going to be impacted in a consistent way so that we know that they're all running the same numbers, is a pretty strong case, and people kind of grok that and get on board with it. So, if you have a structural model and a lot of analysis models, we've done it, we've had a lot of success. A lot of times people think, hey, MBSE, let's, this project did something with MBSE, you're doing something with MBSE, let's put those two models together and we'll have a better overall model. We've been trying that with, we had an institutional effort here where they were trying to capture our operation systems, and we're trying to basically leverage that information that they have to build up the model of our Europa operation system. And we're making progress, but there are some challenges that people often kind of overlook. When you look at an MBSE model, it has a certain semantic that it uses to actually capture the system. And if there's inconsistencies in that semantic between your model and somebody else's model, then you somehow have to make those semantics consistent. There are obviously a lot of standards like SysML and others that can help you with that. But in general, there's always little deviations and tweaks that you need to address. And so that can make, just putting two models together challenging. Another issue is overlap and duplication. So at least I haven't had the experience where the two models are really separate and you just stick them together. A lot of times you have to identify, well, they're both talking about the flight system. How do I put that together? Are they talking about overlapping things? Do I just merge them? Do I delete some? And so it still can be a significant manual effort to try to put those two things together into an overall model. It's definitely one of the kind of the value points or goals of MBSE, but it's still something that is a challenge.